So this is a problem from the 2011 AP Calc BC exam. It's problem number 6. It's a no calculator problem, and as number 6 usually does, it involves a series. And this is kind of a goofy starting point that they give us here. They give us this graph, and if you look at how that graph is labeled, it's a graph of the fifth derivative of x, but after taking the absolute value of all those derivative values. So it's really kind of an obscure graph. We won't need this graph in the majority of the problem. We'll only need it for one of the four pieces. So I'm going to pretty much stay scrolled down the majority of the time, and we'll kind of refer back to the graph as needed a little bit later on in the video. What they tell us in the problem statement here is that f of x is given by this function, sine of x squared plus cosine of x, so a pretty involved function. And then, yeah, they tell us that's the graph of the crazy absolute value of the fifth derivative like we talked about a minute ago. In part A, it says write the first four non-zero terms of the Taylor series for sine of x about 0. So it's really a Maclaurin series. And if you know the Maclaurin series general form for sine of x, all you have to really do is apply the first four values of the index, and that gives you the first four terms of the Taylor series based at 0. So the Maclaurin series for sine of x. They want you to use that as kind of a starting point to develop the series first four terms for sine of x squared. And so if we have a series that converges to sine of x, and we want a series that converges to sine of x squared, only difference between sine of x and sine of x squared is we see x squared has replaced the x. So the only difference between the series that's going to converge to sine of x and the series that's going to converge to sine of x squared is going to be that the x in the series is going to get replaced with x squared. So I've replaced this x with x squared, so grouping symbols are pretty crucial here. And if you simplify, when you raise power to a power, you just multiply your powers. And so you're going to get x to the 4k plus 2 as the new power on x in the Maclaurin series for sine of x squared. And then what are the first four terms? We'll just apply the first four values of the index using this new rule that we just developed, and you have those first four terms. Part B asks us to use our result from Part A to write the first four non-zero terms for the series about f. I guess I kind of overlooked the beginning of part B here, which says to write the first four non-zero terms of the series for cosine of x. So this is just like the first half of part A. If you know this Maclaurin series for cosine of x, the general form is here. Apply the first four values of the index, you get these four values. Then it says use your result from part A combined with these four terms to write the first four non-zero terms of the Taylor series for f. So here's f. So if we have a series representation for sine of x from part A, and we have a series representation for cosine of x from the first half of part B, all we have to do is add those two series representations together, and we're going to have a series representation for the sum of those two functions. And so here were the first four terms of that series at the conclusion of part A. Here were the first four terms of the series for cosine of x. Now we have a little bit more than we need right here. We want the first four non-zero terms of the Taylor series for f. And so the first four non-zero terms are going to be the first four powers of x that are represented in that series. I guess I said that poorly. Numerically, the first four powers of x that are represented within that series for f of x. So as I kind of look at the pieces of the series for sine of x squared, and I look at the pieces of the series for cosine of x, the lowest power of x I see is an x to the 0. So my first term in the series for f is just going to be this 1. My next power of x that I encounter here is an x squared and x squared here as well. So if I combine the 1x squared here plus the negative 1/2 x squared from the series for cosine of x, I get positive 1/2 x squared as the term that involves x squared in the series for f. I don't have anything until a sixth power in the series for sine of x squared. I do have a fourth power in the series for cosine of x. So the next term in the series for f is going to be 1 over 4 factorial x to the fourth. And then the last term is kind of ugly because we do have an x to the sixth term in the series for sine of x squared. We do have an x to the sixth term in the series for cosine. If I combine those coefficients, I'm looking at negative 1 over 3 factorial and then plus negative 1 over 6 factorial. So combining those gives me this ugly expression right there. If you want to simplify that, you definitely can. on the AP exam, when that thing is graded, as long as you have a correct form of the final answer, even if it's unsimplified, you will get full credit. So you might not want to waste the couple minutes trying to find your common denominator and doing the work with this that you'd have to do to combine those two fractions. In part C, we still don't really need to reference that graph at all. We haven't had anything to do with the fifth derivative yet. What they ask us to do in part C is they ask us to find the value of the sixth derivative evaluated at 0. And so this is something that, to do it directly, it's going to take quite a bit of work, because you're going to need to take 6 derivatives of this. You're going to have to start using chain rules for the derivative of this. And after that first chain rule, you're going to have a product. So it's going to be chain rules and product rules from the first derivative onward. So that's definitely not going to be the best way to go about this. It's not wrong, but you're not going to have the time to do that on the AP exam. You want to kind of think a little bit more outside the box here. So what I have listed right here is I have the definition for a Taylor series expansion for the function f. Not this specific function f, but in general a function f. To expand a function with a Taylor series, we're going to take a bunch of derivatives, evaluate those derivatives at c, divide those values by k factorial, and then multiply that by x minus where the series is based to the kth power. Well, if our series is based at 0, as the series we wrote out in part B was, what we know from part B, so I'm kind of skipping to the second bullet point right here, is we know that the term that had the 6th power on it had a coefficient of that ugly combination of those two fractions involving the factorials that we discussed for a few seconds a minute or so back. Using the index value of 6, so a 6 there, a 6 there, and a 6 there, and the c value of 0, so basing the series at 0, what we end up with as the index value of 6's term from this definition is we end up with the 6th derivative evaluated at 0 divided by 6 factorial times x to the 6th power, x minus 0 to the 6th power. I know that that series from part B, which had this as the term involving the x to the 6th power, is a Taylor series based at 0. If I was building that Taylor series from scratch, this is how I would have had to go about producing this term. So I know that if I equate this term with this term in my Taylor series expansion for f, I'm going to have an equation that has within it the 6th derivative evaluated at 0, and that's what we're looking to find here. So if you equate the term from the general term from the definition of a Taylor series expansion with the specific x to the 6th term from the series we just wrote out in part B, you can solve this for the 6th derivative evaluated at 0. Divide both sides by x to the 6th, and those go away. And then if you multiply by 6 factorial, the 6th derivative evaluated at 0 is going to end up being 6 factorial times this ugly quantity. Again, you don't necessarily need to simplify this. This would definitely receive full credit, but if you want to take the time to simplify it, this is a little quicker than finding that common denominator that we talked about at the conclusion of the last part. If you distribute this in, what you end up with is you end up with 6 factorial over 6 factorial. Well, that's just going to be a minus 1 for the second term. And then 6 factorial over 3 factorial. Well, this is 6 times 5 times 4 times 3 times 2 times 1. This is 3 times 2 times 1. So doing the cancellation just leaves you with 6 times 5 times 4, which takes you to 120. Make the 120 negative, subtract 1 from it, and you get negative 121 for the 6th derivative evaluated at 0. So thinking outside the box a little bit, this wasn't that bad to find. It's a lot more quick to find it the method that we showed, with the method we showed here, as opposed to doing this directly. Taking 6 derivatives of this is not going to be efficient at all. In the last piece of this, we're finally going to need to use this graph. And so they say p sub 4 of x is the 4th degree Taylor polynomial for f based at 0. Using the information from the graph, show that the error between using the 4th degree polynomial to approximate f of 1/2 and the actual value of f of 1/2, that value is less than 1/3000th. And so if you think about what Taylor's remainder looks like, Taylor proved that there is an exact difference between the approximation and the function value we're trying to approximate that's made up by this expression right here. So the nth degree remainder would be the next derivative evaluated at z, and z has to be somewhere between where your series is based and the value that you're making an approximation at. Our series is based at 0, and the value that we're making an approximation at is 1/4, divided by the next factorial times x minus where the series is based to the next power. And so if we're doing a 4th degree remainder, we're going to be dealing with a 5th derivative evaluated at z. We're going to have a 5 factorial in the denominator. We're going to have a 5 as the power. We approximated at the x value of 1/4, so I definitely put 1/4 in place of x, and our series was based at c, so 1/4 minus 0 is just 1/4. So this is what will make up the exact difference between p sub 4 of 1/4 and f of 1/4. It's next to impossible to find what the value of z is that makes up that distance perfectly, but what we usually do to bound our error is we build what's called a Lagrange error bound, which would be the maximum value of this expression given the interval where z has to come from. I don't know why I have a 1/2 there. That's really supposed to be a 1/4, so let me fix that. So z has to be between 0, where the series is based, and 1/4, the value that we're approximating at. So if I'm trying to figure out what the maximum value of this is, I need to know I know the value of this. I know the value of this. The only value that's moving that causes this numerator to change is z. Well, if I'm trying to find the maximum value of the 5th derivative evaluated at z, given that z has to come from somewhere between 0 and 1/4, let's go check out this graph. So on this graph, the x equals 0 value is obviously there, and the 1/4 value, if you think about the scaling, is right here. So you know that the biggest value, the 5th derivative, the biggest absolute value the 5th derivative ever takes on the interval 0 to 1/4, happens at 1/4. What is that value? I don't know, 32, 35, something like that. You know it's less than 40, right? This error is clearly less than 40. So it's pretty safe to say that the biggest this value ever gets is somewhere beneath 40. So to bound our error, what we can say is we can take 40, and I've taken 40 because it's going to be simple to put 40 into that numerator and simplify a fraction that has a denominator of 120. Right? 40 divided by 120 is really just 1/3. The only other piece we have is this 1/4 to the 5th power. So if you work out what 4 to the 5th power is, that gives you 1024. And if we multiply these denominators together, we're going to get a denominator that's above 3,000. So if our maximum error is 1 divided by a number that's bigger than 3,000, what we've just shown is that our error is definitely smaller than 1 over 3,000, since 1 over a number slightly bigger than 3,000 is a smaller numerical value than 1 over 3,000.